Good evening, everyone. We are in the week 12 problem solving session of the NPTEL course Control Engineering, and week 12 is about design using state space. I am Teja Golla, a fifth year research scholar working under Professor Santanu Kapat at Embedded Power Management Lab, IIT Kharagpur. Let me share my screen. I hope you can see my screen. But before we start with the week 12 content, I would like to quickly summarize what we have discussed in the previous week, which is week 11, because whatever we'll be discussing in this week is somewhat related to the previous week. So I would like to summarize so that we can brush up what we had discussed in the earlier session. Then we can move on to the week 12 content and then we can learn how to design using the state space. So in week 11, we have started with the state space modeling. So first we have identified the advantages as well as the disadvantages of the transfer function based design. So we have seen the transfer function based design is very dominant approach, and also it is widely used in the industry even till today. Even in complex systems, people use transfer function based design by linearizing the nonlinear model because it is very easy to understand as well as it is very easy to design. And it is widely used, and also because of the algebraic property of transfer function, it makes our life simpler to design the controller and then see how things are going. But the only few disadvantages are that it is applicable to linear systems, although any nonlinear system can be linearized and still we can apply to that. But whenever there are multi-input multi-output systems, then transfer function based design can become cumbersome because there will be multiple transfer functions with all the permutations and combinations possible from each of the input to each of the output. So we have, with these disadvantages, we have seen that state space model could be better in such applications where the number of inputs as well as outputs are multiple, and also the system is non-linear system. So here we have defined the generic form of a state space model where x are the states, u is the input, and y is the output, and x dot is the rate of change of states. So x dot is equals to x plus bu and y is equals to cx plus du. Here we have considered n state. So it's an nth order system and we have considered single input, although it is equally applicable for multi-input systems. And we have defined this ABCD matrices. And then in order to get this state space from a differential equation, we have seen how we are getting the state space equations from a differential equations. So we, based on the order of the system, we have considered the states and then we solve for the ABCD matrices. And then coming to the state space to transfer function, from given state space we can get the transfer function, and it is obtained by this expression c into sa minus a inverse into b plus d. Then we have solved one problem based on that. Then we have moved on to linearization, because if a system is nonlinear, how do we linearize, how to get the Jacobian matrix, how to get the equilibrium points, and how to check the stability. And then we have solved one problem with three different cases, and we tried to correlate the theory that we have learned with the problem and applied the theory in a practical problem. Then we have discussed about the canonical forms, which are controllable canonical form, observable canonical form, and diagonal canonical form. So in controllable canonical form, we have seen that we have to see the given transfer function and then cross multiply and then take the states, and then we'll get the controllable canonical form, and from there controllable canonical form we'll get the observable canonical form by transposing the matrices, and then with the help of dual principle. And then for diagonal form we have to segregate the factors and then apply partial fractions, and then individually we'll get the equations, and then we'll get the oral matrix where each of the states are decoupled with one another. Okay, so now we have also discussed towards then the matrix exponential, how to calculate it using Laplace inverse, and we have solved a couple of problems based on that, and then we have obtained how to get the matrix exponential. So this is all about week 11. Now moving to week 12. So I hope you can see my screen. So first thing is the controllability. So let me consider the same generic expression, which is x dot is equals to x plus bu and y is equals to cx plus du. Okay, so let me consider the system x dot is equals to ax plus bu and y is equals to cx plus du. So what is controllability? So for this, let us say our system order is second order. Okay, say it's a second order system. So which means we have two variables. x1 and x2. So now if we see the phase plane where we are checking, let me draw the phase portrait. Okay. So we have variables x1 and x2. Say this is x1 and this is x2. So now we are trying to move from one point to another point. Say we are trying to move from here to here. Say this is my x1 comma x2, and then this is my x1 dash comma x2 dash. So if I can move or transfer the states from one initial condition to one final condition with the help of input. So basically we are trying to control the destination with the means of input. So if we are able to do that, then we can say the system is controllable. So if the states can be transferred from a given initial condition to a final state by means of the input, then the system is controllable. So in this case, we can say the system is controllable. But how do we know or how do we check a given system is controllable? So that is the question, because we are trying to say that say if the system is second order and we are able to control the systems, say if they are starting from an initial condition and we are trying to control where they will be going, then in that case we can say by means we are controlling by means of input, and then we are controlling its behavior or its destination, then we can say the system is controllable. But all the states may not be controllable, and sometimes maybe few states may be controllable. So how do we know whether the system is controllable or not? So for that we can run a test, and then we have to check the controllability matrix, and then we have to check the full order of the system to see whether the matrix is controllable or not. So let us quickly do that. So there is controllability condition that we can check to see whether the controllability condition. Okay, so in this condition, we'll check whether the system is fully controllable or not, and based on that, we can comment whether it is controllable or not. So in this regard, I would like to give an example what Sir has also given, and it's kind of very easy to understand because it's such a practical example. So Sir has said, assume there is a class and there is one teacher and then two students are there. So now it is easy for the teacher to control both the students so that they will not make noise or disturb the class. Say the number of students have increased to 10 members, and then same teacher is there. So it is still easy to control 10 of them because the number of state variables are less, and he or she can easily control the class by making sure they don't talk to each other or don't make noise and disturb the class. So now let us assume the class strength has gone to say 100. Now it becomes very difficult for the professor to control all the 100 students because some of the students are far away from the teacher and they might be talking to each other, chit chatting, or maybe making noise or using their mobile phones, and he may not be able to control all the students, but he may be able to control some of the students, right? So there are some students who don't make noise and there are some students who make noise, and out of all this sir will be still able to control some of them, and he may not be able to control rest of them. So here say we consider the students as states, say 100 states. Some of the states are controllable by the input. Here input is sir or the teacher, and the other control variables or the other states or the other students are not controllable. So now if we consider two inputs or say three inputs, now we consider three teachers are there and then 100 students are there. So now it may be possible for the for the teachers to control all the 100 students, because now the number of teachers have increased, so the number of inputs have increased. So now using more number of inputs, we are trying to control the states, all the states or all the students here. But say the students have increased to 500 now. Now three teachers may not be sufficient because the class strength is too much and it will be very difficult to control the states. So now the number of uncontrollable states or students may be quite large, and there will be interaction between these controllable as well as uncontrollable students, and then there might be little bit chaos. But now in order to control them, we need more number of inputs or more teachers. But given say we have three teachers only, then it will be difficult to control the entire class. And so that is one case where we have seen a system which is controllable and a system which is non-controllable. So maybe in such cases we might have to uh, take some inputs or some kind of warn the students to make sure the class goes peacefully without any disturbance. But nevertheless, there may be disturbance, and it may be difficult to control 500 students with only three teachers or lesser than that. Yeah. So now let us check the controllability condition. So again, the same matrix I'm taking, x dot is equals to ax plus bu, y is equals to cx plus du. So the controllability condition is that we consider a matrix, say controllability matrix C. The matrix is B, A B, A square B, up to so on A to the power n minus 1 B. So this is the matrix that we'll be considering, and then we have to check the rank of this matrix and then see whether the rank is full or not. So if the rank is full, then it means the system is controllable. But say if it is not, then you have to check which states are controllable and which are not. So here, what do we have? The matrix, right? So now you have to check the order of the matrix. Check the order of matrix. So again, there will be two conditions: either it is full order or it is not. Full order. System is controllable. Sonal, I hope you are able to see my screen. No issue with my audio and video, right? Not the order, rank of the matrix. So it is wrong nomenclature. Say rank is equals to n. So we are considering n state, right? Say rank is equals to n, and rank is less than n. So then system is not fully controllable. So here only few states are controllable. Yeah. So we have discussed till now the controllability aspects. So we have seen that for a given system, what is controllability? Controllability is that if we can transfer the state from one given initial condition to a final state by means of the input, so we are trying to control the destination of the states using input. So if we are able to do that for all the states, then the system is controllable, all the states are controllable. And for that to check, we'll consider this controllability matrix, which is b a b a square b into a to the power n minus 1 b, where n is the order of the system. And you have to check the rank of this matrix. If it is rank is equals to n, then it means the system is controllable. If it is not, then all the systems are not controllable. So depending upon the rank, we have to see how many of the states are controllable and how many of them are not. So in this way, we can see whether the system is fully controllable or not. So if you have any doubts till this point, you can ask, as we'll solve a couple of problems before we move to the observability topic. So any questions till now? Okay, no questions. Then we'll move to the first problem of today's session. Check the controllability of the following system. So here they have given one question with A and B matrices where A is 0, 1, minus 2, minus 3 and B is 0 and 1. So let me rewrite them. A is nothing but 0, 1, minus 2, minus 3 and B is 0, 1. Okay, so we have to check the controllability matrix. So let me copy that. We have to check. So first let us check what is the order of the system. So order of the system, which is n is equals to 2 because the order of the A matrix is 2. So now our n minus 1 will become 1. So the controllability matrix that we will be checking is B as well as AB. So B is given, we have to calculate AB and then we have to check the rank of the matrix. So let us calculate AB. So AB is nothing but 0, 1, minus 2, minus 3 into 0, 1. So the first row will be 1 and second row will be minus 3. So this is my AB. So now let us check what is my controllability matrix. So controllability matrix is B, which is 0, 1. AB is 1 and minus 3. So how do I check the rank? I'll calculate the determinant of this matrix. So find the determinant. And then see whether it is equal to 0 or not. So if I calculate the determinant, I'll get determinant of C matrix is 0 minus of 1 minus 1. So it is not equals to 0. So the rank of the matrix, so the rank is equals to 2, which is same as the order. So the system is controllable. So the system is controllable. So what we have done in this question, so in this question they have given a system with A and B matrices, and then they have asked whether the system is controllable or not, and we have started with the theory that we have learned to check the rank of the controllability matrix C. So C is B, A, B up to 1 a to the power n minus 1 into B. And in this case or in this question, n is 2. So we have to just calculate B as well as AB because n is 2, n minus 1 is 1. So B is given, I have calculated AB. Then I got the C matrix, which is B as well as AB. And in this matrix, now I have calculated the determinant to see whether the determinant is 0 or not. If the determinant is 0, rank is 1. If it is not, then rank is 2. So rank here is 2 because determinant is not equals to 0. Rank 2 means rank is same as the order of the matrix, which means it is full rank. And it means the system is controllable. So this question, if the A and B matrices are this, then we will be able to control both the states by means of the input. So this is about controllability. Let us also discuss the code. So I'll put a heading controllability. So this is the MATLAB code to check the controllability of the matrix. So first I'm clearing as well as closing all the workspace and clearing workspace as well as command window and closing all the plots. And my A matrix is what? 0, 1, minus 2, minus 3. So it is, uh, so this is observability. Okay, this is controllability. I think I have messed it up. Observability, controllability. Okay. So and this is observability. Yeah, sorry for that. Observability. Okay. So controllability. So my matrix is 0, 1, -2, -3. So 0, 1, -2, and -3. And B is 0 and 1. So I'm checking the controllability of this matrix. So there is a command to calculate the controllability matrix, which is CTRB controllable A comma B, and then we can display the controllability matrix, which is C naught, and then there is this command rank of C naught, which will give the rank. So based on the rank, now we can say whether it is controllable or not. So let us run this. Okay. So let us run this. So the controllability matrix is 0, 1, 1, and -3, which is what we are getting 0, 1, 1, and -3. And the rank is 2. If the rank is 2, it is full rank because the order of the system is 2. So now we can say that the given condition or the given system is controllable. So this question, the system is controllable. I hope the concept is clear. If you have any doubts, you can ask. So now let us quickly solve another problem. Check the controllability of the system. Here A and B are different from what we have considered previously, and the order of the system is same. So A is 1, 0, 0, and 2, and B is 1 and 0. Okay. So in this question, the order is the same as previous question. So the controllability matrix C is B, A, B. Okay, let us calculate it. First, B is given. Let us calculate A, B. 1, 0, 0, 2, 1, 0. So the first row will be 0. Second row will also be 0. So AB is 0. Okay. So now what is the controllability matrix in this case? B is 1, 0. AB is 0, 0. So now we can see the determinant of C is 0, right? Determinant of C is 0, which means rank is not 2. But is there any non-zero element in the matrix? Yes, so 1. So the rank is 1 and not 2. So that means in this case, rank is 1, which is less than 2, which means it is not fully controllable. So all the states are not controllable. Some are uncontrollable. So all the states are not controllable. Some states are uncontrollable. Okay. So rank is 1 and it is less than 2. So we can say that the system is not controllable, and some states are uncontrollable, some are controllable. Here there are two, so maybe one will be controllable, one will be uncontrollable. But before we see which is controllable and which is not, let us solve, let us go through the MATLAB code and then check whether what we have done is correct or wrong. So A matrix is 1 and 0, 1 and 0, and B matrix is, sorry, 0 and 2 is also there. Let me enter those, 0, 2, and B matrix is 1, 0. Okay. So our A, B matrices are there. Let us run. So the controllability matrix is 1, 1, 0, 0. I think we have made one mistake. So so I made a mistake in A, B calculation. So this element is 1. So this element is also 1. Sorry, my bad. This is 1 and this is 0. So sorry again. This is also 1. Okay. So my AB is 1, 0. Controllability matrix is 1, 1, 0, 0. Still the determinant is 0 and the rank is 1. So I made a mistake in the calculation and I have cross-checked with MATLAB and saw that my there is a small mathematical mistake in what I have done. So it's always good to cross-check and then rectify our mistakes. So or in which way I try to improve myself is, see here I have solved one problem and then I have noticed that I have made an error. So now I'll remember what error I have made. So it is a matrix multiplication. So I will keep this in mind that in the future or in the upcoming problems, whenever I'm multiplying matrices, I'll be more careful because there is high tendency that I'll make the same mistake again. So I have to be more careful. So in this way, whenever we solve problems, we have to cross check and see where we are making the mistake and remember the mistake. So again, in the same instance, now we have to put more efforts and be more conscious about what we are doing so that we'll not make any mistake, and say we have made mistake somewhere else, and then now we have to be more careful when we are in that instant where we have made the mistake. In this way we'll try to improve ourselves, and eventually when we solve more problems we'll feel more confident and less with less mistakes. Yeah, so we have checked the system is not fully controllable and the rank is less than the order of the system. So now the question is obvious, which state is controllable and which is not. So let us write the x dot is equals to ax plus bu. So I'm writing it again here. So x1 dot x2 dot is equals to ax ax plus bu. A is 1002 and b is 1002 1002 and b is 10. 1002 b is 10. Okay. So let us write the individual equation. So from there we can understand which is controllable, which is not. So x1 dot is equals to x1 plus u, and x2 dot is equals to 2x2. So here you can see there is a dependency on the input. Dependency on the input. Here there is no dependency on the input. No dependency on the input, which means this state is controllable because I can control it by giving whatever input is required. So this is controllable. This is not controllable. Okay. So we have seen in a given system, one state is controllable and the other state is not controllable. But by controlling this, whether system is stable or not, that also we should check, right? Because controllability is like the superset. If the entire system is controllable, which means all the states are in my control, I can go from certain point to another point and I can make sure the things are okay, system is stable. But say if it is not controllable, whether the system is stable because I am able to control certain states, but what about the other states? Say if the other states are stable, it will become zero. So system is more or less stable. I will be able to control whatever I can, and whatever I am not able to control, they'll be eventually becoming zero. But say what if the uncontrollable states are unstable? Then even though I'm controlling some states, the other states are exponentially increasing and they're becoming larger and larger. So the system will be unstable. So in that case, how we are going to stabilize? So that's a different thing. But in this question, if you see x dot is equals to 2x2, right? So this is unstable because the eigenvalue is positive. So it is unstable. Okay, so controllability is one thing, and then stability checking is another thing. So we have to check if the uncontrollable states are unstable, system may become unstable because we are not able to control them and they're increasing, right? Maybe unstable. So if the uncontrollable systems are stable, then they will eventually become zero or will reach some state like some value, constant value and fixed. But if they are unstable, we don't have any control on them. and now they are exponentially increasing, so we can't control those states, and in such case the system will become unstable. So in such cases we have to be very careful how we are going to control them. But since that was not discussed in this course, we will not go into that discussion, but we'll just end at this point to check whether system is controllable or not, and which states are controllable and which are not, and whether the uncontrollable system states are stable or not. So we are just checking these kinds of tests, and then we'll leave it there. So now the third problem here, I have considered a third order system. So let us solve this. Controllability same. So now n is equals to 3. So n is equals to 3, which means my controllability matrix will become B, A, B, A square B. Okay, so to avoid the math, because that will unnecessarily waste our time, and then instead of that, we could spend time on the uh, more solving more problems and discussing more theory. So I will not solve individually B, A, B, A square B, because that will unnecessarily consume time. So I have to check whether this rank of this controllability matrix, rank of this matrix, check rank of this matrix. So as I said, two cases is equals to 3 or less than 3. And then this is all states are controllable. Uh, all state, not all states are controllable. Okay, so let us do it or solve it using the MATLAB code itself rather than solving each and every matrix. And then again for rank, we have to calculate determinant. So you can solve the problem during your leisure time, but to uh, targeting to cover more topics and solve more problems, I'll skip the math. So please don't mind. Yeah. A is 0 1 0 0 1 0 0 1 0. B is sorry 0 0 1. Next line is 0. I'll 0 0 1 semicolon. Then we have -6 -11 -6. A is done. B is 0 0 1 0 0 1. Okay, now we are checking the controllability of the matrix. So B is 0 0 1. So first line will be 0 0 1. Next one is A into B. Although we can calculate, I have skipped it. So this is AB, this is A square B, and then the rank is 3 because the determinant of C naught is not 0. Because we can see that these two are 0, so this multiplied by -1. So determinant is basically -1, which means it is non-zero, which means the rank is 3. So the rank of this is 3. So let me rewrite it. So C matrix is whatever we are getting. C matrix. Which C matrix are we getting? C matrix 0 0 1 0 0 1 0 1 -6 1 -6 25. Okay, and we have seen the rank is equals to 3, which is maximum. So the system is controllable. All states are controllable, and which is also, and if you notice, this is controllable canonical form. And then yeah, so if you might have noticed, it is good, else just take a note. So it is controllable canonical form. Yeah, so now we'll discuss about the observability, and then we'll also see how to, because we are understanding how to control the states, but there is also how are we going to control, right? So we are checking whether it is controllable or not. but we should also discuss how are we going to control them. So that's a different topic we'll dive into once we finish the observability test as well. So this is all about controllability. So just to quickly summarize before we move further, controllability is like when we can control the state and then make sure that they transfer from one initial condition to final condition by means of the input, then it is controllable. So in order to check that, we have to check the rank of this controllability matrix. If it is equal to n, then all states are controllable. If it is not, then only few states are controllable. And we have solved a couple of problems where I have considered one second order system which is controllable, and then another second order system which is not fully controllable, and we have seen which state is controllable and which is not. And in the third problem, we have seen a third order system which is controllable and all states are controllable because the rank is 3. So now if you have any doubts, you can ask, else we'll move to the next topic, which is observability. Okay. Yeah, so we'll try to correlate all these things. Controllability is like which all states we can control. Observability is like which all states can we observe, or which all states can we measure. So it's all about measuring the states or observing the states, whether we can measure or observe all the states. Observe means we are trying to measure. So whether we can measure all the states. Yeah. So again, same test. How do we check? How do we check? So here we'll check the observability matrix, rank of the observability matrix. So the state or the, if we consider x dot is equals to ax plus bu and y is equals to cx plus du, the observability matrix O is nothing but C, CA, CA square up to so CA to the power n minus 1. So we are checking the rank of this matrix. Again, as we said, there will be two cases where rank is n, where rank is less than n. So if the rank is equals to n, or if the rank is less than n. So if the rank is equals to n, it means all states can be measured. All states can be measured. But if it is not, so not all states can be measured. Not all states can be measured. Some are measured, some can be measurable, others are not. So not all states can be measured. So the question is, what about the states that we cannot measure? Yes, right? The basic question. What about the states? What about the states that we can't measure? That we can't measure. So in that case, we estimate them. Okay. We estimate those states. Okay, we try to estimate using observer, and then we get the estimated states, and using those estimated states, we'll try to design the controller. Okay, so just to quickly summarize again what we have discussed. Previously, it's about controllability matrix. Now we are discussing about the observability matrix. So in this observability matrix, we will see whether we are able to check. How we are going to check basically is we'll check the rank of the observability matrix. So here the rank or the observability matrix is C, CA, CA square up to so C to the power C into A to the power n minus 1. And we'll check the rank of this matrix. If the rank is n, all the states can be measured. If it is not, then not all states can be measured. But in such case, what are we going to do? In such case, we'll have to estimate those states which can't be measured. Because say I am measuring some current or voltage, then I'll get the information. But say I'm not able to measure that, not able to get that, then how are we going to do? Then we have to estimate it by some means. So using the other states or some information, we'll estimate it and use it as a part of our controller. So again, we'll solve a couple of problems before we move into the design part so that our concepts will be cleared. So here I have given one question where I have said that check the observability of the following system. So what is the order of the system? The order of the system is 2. So n is equals to 2. So now I have to calculate C as well as CA because A to the power n minus 1 is A because n is equals to 2. So here order of the system is equals to n is equals to 2. Right? So order of the system is 2. So now my observability matrix will become C as well as CA. C is already given. I have to calculate CA. So let us calculate CA. CA. C is 1, 0. CA is 0, 1, minus 4, minus 5. So if I multiply, what will I be getting? So just to check, this is 1 cross 2. This is 2 cross 2. So eventually I'll get 1 cross 2. So the first element is 0 and the second element is 1. So we'll get 0 and 1. So CA is 0, 1 and C is 1, 0. So my observability matrix O is C is what? 0, 1 or 1, 0, 1, 0 and CA is 0, 1. So if you check the determinant is non-zero, right? Determinant is equals to 1. Determinant delta is equals to 1. So the rank is 2 because the determinant is not 0. So rank is 2. So it is observable. It is observable. The given system is observable. Okay. Yeah. So now that we have obtained this, so this is the given question. A, B, C, D matrices are given, and then we are trying to check the rank of the observability matrix, and we have obtained that the rank is 2, which is same as the order of the system, which means full rank, and the given system is observable. So let us quickly solve the same problem using MATLAB. So this is the controllability code, and similarly we have the observability code. Again, I'll upload all this code so you can also play with these codes once I upload it to the drive. So my A matrix is what? A matrix is 0, 1, minus 4, minus 5. 0, 1, minus 4, sorry, minus 5. C is 1, 0. And again, here controllability has CTRB, observability has OBSV. This is the command, and then it will directly give the matrix which I am displaying, and then rank also I am displaying. Okay, so the observability matrix is 1001, which is what we have obtained. And since the determinant is non-zero, the rank is 2, which means the given system is observable. So we have done it by hand, and then we are cross-checking using MATLAB. So it will be easy for us to, you know, to be confident, and then we can see whether we are making any mistake, and we can also correct ourselves. Yeah. So now let us solve one more problem. So if you have any doubts, you can ask, else I'll move to another problem. Any doubts so far? Okay, I guess no. Okay, so in this case, we have A, C, D, because B is not needed. I have not given B in this question. So A and C and D are given. D is 0. So output is not related on input. So we have to check the observability matrix C as well as CA. So the observability matrix O is C as well as, sorry, C as well as CA. Okay. So now C is 10. So CA is what we have to calculate now. CA is 10 and A is 1002. So the first row will be 1, second row will be 0, I guess, right? 10, 10. Yeah, second row, yeah. So it is 10. Now let us see what is the observability matrix O. So observability matrix is first row is C, which is 10. Second row is also 10. So if you can see there is repetition. Two rows are same, basically dependent, which means determinant is 0. Again, we can calculate that. So determinant is equals to 0. So it is not having the full rank. And if we have to check the rank is 1 because there is one non-zero element. So the rank is 1, which is less than 2, the order of the system. So it is not fully observable. Some of the states are not observable. Only one of them is observable. Not fully observable. So basically, we are checking the matrix and then the rank so that we can see whether the system is observable or not. But as the order of the system increases, you can do the same for the higher order system. But we have started with second order because we can calculate it. And for third order, I'm using the MATLAB to save time. But during your leisure time, I request you to do the same experiment in your house or hostel and then cross check your calculation with the MATLAB. So let us quickly check whether this is observable or not. So we have 10 as well as 02. So let us check that. Yeah, 1002. Okay. And C is 10. Okay. So yeah, let us run it and then see whatever we are getting, it is matching or not. So observability matrix is 1010 and rank is 1. So the order of the system is 2, whereas the rank of the system is 1, which is less than the order of the system. It means the system is not fully observable, which is again what we are getting. So we have solved few problems where we have checked the controllability of the system, where some of them are not controllable, and we have also checked observability of the system where in the previous question the system is observable, and in this case it is not fully observable because the rank is 1, which means one of the state is observable and the other one is not. So in this way we'll check the observability as well as the controllability, and then based on that we'll have to take action. Say we are trying to design a controller and trying to control all the states. So the first thing we have to check is whether all of them are controllable. In that case only we can control it. So we'll see if it is, then we'll proceed with the controller design. Again, we'll be discussing how to design the controller. But say some of them are non-controllable, then the obvious question to check whether they're stable or not. And if they are not, then we don't have any control on the states. But if it is, then we'll see how we can do. Similarly, if we are trying to use a state feedback based approach, then we need to have the information of all the states, which means we are or we should be able to measure all the states. And when we are talking about measuring something, again we are coming back to the same concept that whether they are measurable or whether all of them are observable. So now the observability will come. So we have to check how many of the states are observable, which means how many of the states can be measurable. Say all the states are measurable, then we can do full order state feedback, and then we'll have the information of all the states, and then we'll have more flexibility, I would say, or more degrees of freedom to control all the states. But say in a third order system, we are able to measure only two, then we might have to estimate the other state or we have to see whether we will not be able to estimate or we will be able to estimate. And then maybe in that case, we have to use a reduced order state feedback or simply output feedback, where output is one of the state. So we can do output feedback or state feedback or reduced order state feedback. So in this way, we'll be able to proceed further. So at each point, we have to check uh, all these things using the tests that we have discussed, by checking the rank of the observability matrix, by checking the rank of the controllability matrix. But again, nevertheless, we'll be able to identify which state is controllable, which state is measurable. So accordingly, we'll be taking the action. And eventually, I think I have one more problem on the observability, which is third order. We'll also solve this, and then we'll move to the next discussion where we will be learning how to design controller state feedback, and then we'll see how to place the poll placements, and then we'll get more insights regarding that. So the meeting will be, I think, ending within a minute. So if you have any doubts, you can ask, else let the meeting ends. Once the meeting ends, we can join back, and then we can solve this problem. So any questions till now? I hope you are following. Revant and Power. Okay, I think they have mentioned something. Revan says yes. Okay. So, yeah, the meeting is less than a minute. Let it end. We can join back and then solve this problem. So, I hope you are also going through the other videos that I have uploaded. And how are you doing in your assignments? All good, or any difficulty that you are facing? So, if this meeting ends, kindly join back. Any issues are you facing with the problems, assignment problems? Facing any difficulty? Yeah. So, Revan says no. Okay. So, I guess. Things are okay. So are these lectures, are these problem solving sessions helpful? Yes, sir, helpful. Okay, okay, good, good. Okay, let this meeting end. We'll join back. So let us solve the sixth problem of today, where I have given A, B, C, D matrices, and then I'm asking whether the system is observable or not. So let us see, because the order of the system is two. Now we might have to calculate more number of matrices. So the order of the system is n, which is equals to 3. So now observability matrix that we are supposed to calculate will be C, CA, CA square, which is n minus 1, 2. So now we have to calculate C, CA as well as CA square. So because C is there, let us calculate CA and let us use MATLAB to calculate CA square. Okay. So CA is what? 100 into 010 001 minus 2 minus 5 minus 4. So the first row will be 0. Then second one will be 1. Third one will be 0. So CA will be 010. So my observability matrix, again CA square I will not multiply because it, or maybe let us multiply. There is no issue. Hopefully things are simpler. So A square is 010 001 minus 2 minus 5 minus 4 multiplied by 010 001 minus 2 minus 5 minus 4. So the 010 010 will be 0. Then 010 into 010 will be 0. Then the last one will be 1. And the 001 001 001 001 minus 4. Now it will be minus 2 minus 5 minus 4 into this. It will be 8. Then 20 minus 2, 18. Then last one will be minus 5 plus 16, 11. So A square is this. Now let us multiply CA square. So C into A square. So CA square is 100. Hopefully I have not made any mistake, but again, we'll cross check using MATLAB. So it will be 0, 0, 1 again. Okay. Yeah. So now let us write the observability matrix O. So C is what? C is 1, 0, 0. Then we have 0, 1, 0 and then 0, 0, 1. So identity matrix. Very good. 1, 0, 0, 0, 1, 0, then 0, 0, 1. So we got the identity matrix. So the determinant is 1. We know that implies rank is 2, rank is 3. So it is fully observable. Okay, so the entire system is fully observable. But let us again cross-check the same using the MATLAB. Observability A matrix is what? A matrix is 0, 1, 0, then 0, 0, 1. Okay, then last row -2, -5, -4, -2, -5, -4. Then C matrix is 1, 0, 0. And then let us run and see whether the observability matrix that we have calculated is the same or is it any different. So we have 1, 0, 0, 0, 1, 0, 0, 0, 1. So the math is correct. Observability matrix rank is 3, so which is also what we are getting, and it is fully observable. So in this way, we can check the observability as well as the controllability of a given matrix, and then we can design the controller accordingly. So is this clear until this point? Any doubts so far? Now we can move to the design part. Okay. Yes. So I guess no doubts. Then let us solve or let us move to the state feedback control. So again, we'll see how we are correlating both observability as well as controllability, and then we'll see. So we'll discuss about the pole placement also. Okay. Say we have a given system x dot is equals to ax plus bu, y is equals to cx plus du. Now, basically, what we are trying to do is we are trying to feed back the system. So we are trying to feed back the states. So we are trying to feed back the states as the input. So that's why it's called state feedback control. So the input to the system U is nothing but a product of the states. So we are feeding the states back to the system, and that's why it is called state feedback control. So what we are trying to do is we are trying to do U is equals to minus kx. So U is equals to minus kx. Uh, and then we'll substitute and see the x dot. So x dot is ax plus b, U is minus kx. So ax minus bk x. So now if I calculate, I'll get my x dot is equals to a minus bk into x. Yeah. So now this is my closed loop system, right? This is my closed loop because U is feed, it's a feedback. So this is my closed loop systems. Okay. So, but now, where does the pole placement method come into picture? Where are we even actually getting the pole placement into the discussion, right? That's an obvious question. So, for this closed loop system, there are eigenvalues, right? This how to calculate the eigenvalues? So, eigenvalues. So, determinant of lambda I minus a minus bk. So if you equate it to 0, then you can get the closed loop poles, or I would say eigenvalues, closed loop eigenvalues, or desired pole locations, right? If we solve desired pole location. Now we are giving the desired pole location. Sorry. So what we are doing is we are giving the so so this is user's choice. Now we are giving the desired pole location. So we know the characteristic equation. So because user is giving the desired pole location, we can get the characteristic equation. So we can calculate the characteristic equation. We can calculate the characteristic equation. And then we have to match it accordingly, or we have to choose these gains, u equal to minus kx, right? So if I write u is equals to minus of k1, k2 up to so on kn into x1, x2 up to so on xn. So these are the unknowns. Now we are trying to calculate these unknowns. So what we are basically doing is uh, we or the user is giving the desired pole locations. And now from the desired pole locations, we will get the desired characteristic equation. So what should be my characteristic equation in terms of lambda or s, whatever we are getting, and k is unknown. So now using this k, we can calculate this determinant, which will be a function of k. However, we know the desired characteristic equation. So then we can compare the coefficients of the obtained characteristic equation with the desired characteristic equation. And then we will be able to correlate or obtain the gains k1, k2 up to so on kn. So once we calculate the characteristic equation, we will compare the obtained versus designed. So then compare the desired characteristic equation with the obtained characteristic equation. Then we have to solve for the unknowns, which are k1, k2 up to so on. Then solve for the unknowns, which are k1, k2, k3 up to so on kn. Okay, so again, if we try to think about the observability, so we are trying to sense all the states and then feeding back as an input to the system. So it is all based on the assumption that all the states are observable or measurable. But what if not all the states are measurable? Then you have to estimate it. So that's where the observer comes into picture. Then you have to estimate the states and then feed the estimated states as the feedback, not the actual ones, but the estimated ones. So in that case, you will have an observer which will try to estimate the states, and then you also have this controller which will use the estimated states as feedback and then will feed as an input back to the system. So that will have the controller dynamics as well as the observer dynamics. And in such case, observer has to work faster than the controller because it is what is giving the data to the controller. So for the controller to compute, it should have the data getting from the observer. So the observer has to be faster so that it will give the real-time estimated data to the controller, and then controller will be controlling the system, and then it will make sure the poles are at the desired location, or it is responding in a desired transient requirements or whatever requirements the user is giving. So if all the states are observable then or measurable, we can get the states which we can use as a feedback to the system. But in the cases where it is not, then you have to estimate it, and that's when the observer comes into picture. But nevertheless, u is minus kx, and if it is estimated, then we'll use x hat. So maybe I'll write the notation. X is the states, and then x hat is the estimated states. So this is what it is followed in the control systems. So x hat, I don't know whether it is properly visible. X hat. Okay, so x hat is estimated state. So in that case, you will have minus k x hat, and x hat will also have the observer dynamics, and then accordingly you will design. So I'll quickly summarize what all I have told till now. So we have a nth order system, x dot is equals to x plus bu and y is equals to cx plus du. And then now we are feeding back the states as an input to the system. So that's why it is state feedback control, and u is equals to minus kx. So u is minus of k1, k2, k up to so on kn into x1, x2 up to so on xn. And x dot now will be a minus bk into x. So now the stability of the system is dependent on the eigenvalues of this matrix a minus bk. So if we calculate the eigenvalues, then we'll get an equation in terms of the unknowns k1 up to so on kn. But if the user has given the desired pole location, we can also calculate the characteristic equation and compare these two equations to get the unknowns k1 up to so on kn, and then we can solve for this and then implement it accordingly. So this is like the crux of the discussion. We have two problems, one problem for the controller design using state feedback and one for the observer. So both are mostly similar but slightly different from one another. If you have any doubts, you can ask, else I will start solving the problems. Any doubts until this point? Okay. So no doubts. Okay. So in that case, let us solve the problem. So just kindly go through the question. Let me take some water. Yeah. So the first one is state feedback based design. Calculate the gains K1 and K2 such that the desired poles are at minus 2 plus j as well as minus 2 minus j. So I think I have missed minus sign here. So let me edit the this minus k1 minus k2, and let us press OK. Yeah. So because it's a feedback, right? Negative feedback system, which we have thoroughly discussed. So it's that's what is stable. Yeah, so this is what we'll get. First, what we are doing, we have to get the controllable canonical form representation, because if you see, it is a controllable canonical form representation. So the uh, like we are not given the state space representation. So we are supposed to calculate the state space representation, and then we'll have to go to the question further, right? So let us see this. This is controllable canonical form. Yeah. So we'll start solving. G of s is what? Y of s by u of s, say. G of s is, or y of s by x of s. It will make our life simpler. Is equals to 4 by s square plus 5s plus 6. So we'll have y double dot plus 5 into y dot plus 6y is equals to 4 into x. Or I think this will make make us more confused. So I'll give it as y of s by u of s because the input. So now it will be simpler, because if I misplace, then it will become more confusing for you. Okay. So y double dot plus 5y dot plus 6y is equals to 4u. Now, whatever we have done last time, we are following the same thing. So just so I'll show quickly, we'll consider y to be x1, y dot to be x2 in the similar way we'll be doing. So yeah, let me go back to the first problem of the last week. The same way we are going to do. Yeah, I think we have. Yeah, so in this way, so we have similar problem. So x1 dot is x1 is y, x2 is y dot, x3 is y dot, and then we'll be able to get this matrix. Okay. So x1 is y, and then x2 is y dot, and then x2 dot will be y double dot. So it's a second order system, right? So we should not consider x3 because there is y double dot in the system. So that's not what we'll be doing, because we have to see the order of the system. The order of the system is 2. So the order of the system is 2, which means we have to consider two states. So one state is y, other state is y dot. So I should not consider x2 dot, because whenever we look at the equation, we will tend to consider x3, which is y double dot, because y double dot is there. But we are calculating x1 dot and x2 dot, and x2 dot itself is y double dot. So no need to consider three states. Two states are fine because it's a second order system. So now if we write the equation, x1 dot will be x2, right? Y dot. And then x2 dot is what we will be getting. X2 dot is minus 6x1 minus 5x2 plus 4 into u. So is this clear? How we are getting this, Revant? Okay, I think he has mentioned in the chat. Yes, sir, clear. Okay. So now we'll write the state space representation. So we have x1 dot, we have x2 dot. X1 dot is x2, so we'll have 0, 1. X2 dot is having minus 6 and then minus 5 into x1, x2 plus 0 and then 4. And this is u. So 0, 1 minus 6 minus 5, x1, x2, 0, 4, u. So this is my A matrix. This is my B matrix. And then if I have to calculate C matrix, y is nothing but x1. So I'll get y is equals to 1, 0, x1, x2, and y is not dependent on u. So I'll have 0 into u. And this is my C matrix. And this is my D matrix. So if you go back to the question, 0, 1, B0, B1, what is B0, B1? B0 is 6 and B1 is 5. So we have calculated B0 and B1. So my B0 is 6 and B1 is, sorry, B, B1 is 5. So first we have calculated the state space representation, which is the basis of the question, because not all the questions they'll give the state space. So the first point is to calculate the state space, and then we have to identify. We have identified it is a controllable canonical form, and based on that we knew that uh, A and B. So I think there is a mistake, right? It should be 0 and 4. I think it is not 0 and 1. It should be probably 0 and 4. Or are we making any mistake? No, right? 0, 1 minus 6 minus 5 and then 4. So it should be 0 and 4, not 0 and 1. I think so. There is some mistake. Sorry. Where is U? U, it is 4. So I think there might be some mistake here. Okay. Yeah, 0 and 4. And then C is 1, 0. So my here there is 4. So there is a direct relation of y of s is what? 4u, right? So there is 4, so it is not 1. It would be 1 when the numerator is 1, but since it is having 4, so we will be having 4 here. Okay, so we have identified it's a controllable canonical form, and we have obtained b0 and b1. So this is b0, 6, and b1 is 5. So now they are asking u is equals to minus k1 minus k2 x1 into x2, because minus k into x, basically k is k1 k2. It's a state, it's a matrix because it's a second order system, two states. And then they're asking what is k1 and k2 such that the desired closed loop poles are at minus 2 plus j and minus 2 minus j. So it's a second order system, right? A minus bk, a minus bk, it's a second order system, and they have given the poles of that. So whatever they have given a minus bk. So let me write the matrices again. So my matrices are A is equals to 0, 1 minus 6 minus 5. 0, 1 minus 6 minus 5, semicolon, and B is 0, 4, and K is K1, K2, K matrix, right? K1 and K2, and U is equals to minus Kx. Okay. So now we have been given A minus Bk matrices. The eigenvalues are given, which are minus 2 plus or minus j. Okay. So minus 2 plus or minus j. So this is minus 2 plus or minus j. So from this we can calculate the polynomial, right? Characteristic polynomial, what is desired. But instead of doing that, again, I have written the MATLAB code. So we'll use the MATLAB code to get the desired polynomial. So the desired poles, closed loop poles, desired closed loop poles are minus 2 plus j, comma, minus 2 minus j. Now, desired closed loop poles are given. Now I have to find the desired closed loop or the desired characteristic polynomial. Desired characteristic from these poles. So I have written a code. I'll be again uploading as I mentioned earlier, and let us use the code. So the desired poles. So clearing the workspace and command window and closing all the plots if they are open. Desired poles are minus 2 plus j, minus 2 minus j. And if these are the poles, then polynomial coefficients are p. And then I'm displaying the coefficients. So let me run it. So it is 1, 4, 5, right? So I think there is a command roots of, I think 1, 4, 5. Let us see if it works. Yeah, so roots command is to get the roots if these are the coefficients. So roots is to get the roots and polynomial is to get the polynomial. So my polynomial is s square plus 4s plus 5. So I can get this s square plus 4s plus 5. So the desired polynomial is s square plus 4s plus 5, and then I have just to cross check, I have cross checked and the roots are minus 2 plus or minus j. So in this way we got the desired polynomial, because if the roots are say higher order and the three roots, then I thought of not wasting time on these things, rather I could spend it on solving the problems and discussing theoretical stuff. So I thought I will try to take advantage of MATLAB, where and all I don't want to waste time in solving the math. That is obvious, and I'm sure you will be able to do. So I'm using MATLAB to save time where all I can, and then I would be maximizing my time in these 2 hours to discuss more theory as well as solve more problems. So that's why I'm trying to make my life simpler, as well as you can also use these codes to practice and then cross check your math. So in this way, I got the desired characteristic polynomial, but I have to calculate K1 and K2, right? But I also know that A minus BK closed loop poles or the characteristic polynomial is should be matching with S square plus 4S plus 5. So I have to calculate A minus BK. So let me copy paste this. I hope it is clear till now, right, Revant? Yes, okay. So this is ABK. Okay, so ABK. Okay, so I have to calculate A minus BK. So first let me calculate BK. 0. So it is just sometimes even I get confused what will be the rank, because that maybe that's how I am. So I'll always write the order of the size of the matrix, so that now I'll know the final one will be 2 cross 2. So I have this thing, I looking at the matrix, I can't immediately say what will be the resultant matrix size. So I have this habit of writing the size of each matrix. So now I'll multiply the size of the matrix, so I know it will be 2 cross 2. So in this way, like I knew where I'm making mistakes. So I also found the solution where I can make myself more comfortable with the matrix multiplication. So if I multiply, the numerator will be 0, 0, and then denominator will be 4k1, 4k2. Okay. So my bk is obtained. Now I have to calculate a minus bk. So a minus bk, let me know if I'm making any mistake. So 0, a minus bk 1, minus 6, minus 4k1, minus 5, minus 4k2. So this is my a minus bk. So if I'm making mistake, kindly let me know so that we'll not end up with the wrong solution. So a is 0, 1, minus 6, minus 5. So 0 minus 0 is 0 and 1 minus 0 is 0. Sorry, 1 and minus 6 minus 4k1 minus 5 minus 4k2. So now let us calculate determinant of s of si minus of a minus bk. So this is the characteristic polynomial, right? So here we'll have s, then minus of minus 1 is minus 1, and here we have 6 plus 4k1. Here you have s plus 5 plus 4k2. So the determinant of this is equal to our characteristic polynomial, which is given by this s square plus 4s plus 5. So this should be equal to this, which is desired, which is given. Now we are trying to see whether, again, whether such k1, k2 exists. That also we have to check, because say here actually in this problem we'll get two independent equations. So we'll always have a solution because both of them are independent. It will have a unique solution. But sometimes if the equations are dependent on each other, or if in certain cases it's either no solution or more than one solution, so we have to also check regarding that, and that will appear when it is not fully controllable. But in this case it is controllable, so you'll see that you'll get two equations, two independent equations, so you'll always get unique solution. So let me calculate the LHS. It will be s square plus s into 5 plus 4k2 plus 6 plus 4k1 is equal to s square plus 4s plus 5. Right? I think I have not made any mistake. So now if I compare, I'll get 5 plus 4k2. So this is what I'm saying. You will get two independent equations. So k2 is nothing but 1 by 4 or 0.25, and then 6 plus 4k1 is 5, so k1 is nothing but, so it is minus 0.25, right? I think I minus 0.25, and then this is also minus 0.25. Okay, so we got k1 and k2. So my k1 k2 matrix is coming out to be minus 0.25 minus 0.25. So this is how we have solved based on the desired pole locations. Right. So basically what we are trying to do in this problem, so a matrix is not given directly. So they have given the differential equation, or I would say transfer function to be precise. And then they have asked us how to solve further k1 and k2, and they have given the desired pole locations. Now we are trying to solve this step by step. So initially we have started with, let me go to the top. Sorry. Yeah. So we have first identified the given state space representation is of controllable canonical form. So we have to identify B0 as well as B1. So once we identify B0 and B1, then only we will be able to solve further, because we need AB matrices to calculate the K, unknown K matrix. So we have written the differential equation, and we have identified the order of the system is 2, which means x1 is, if we consider x1 to be y and then x2 to be y dot, then we'll get this state space representation. From there, I got the A, B, C, D matrices, and then I have calculated the B0 as well as B1 values. And once I got A, B as well as K is given, Now I know the eigenvalues of A minus BK is what my desired pole locations are, which are given as -2 plus J, -2 minus J conjugate poles. And then based on this desired closed loop poles, I have to calculate the desired characteristic polynomial. And instead of solving directly, I have written a MATLAB code where you give the desired poles, which is saved in P, and then this poly of P will give the coefficients 145, which I am saving in coefficient. So this coefficient is 145 and it is from the increased order. So this will be constant. This is coefficient of S. This is coefficient of S square. So S square plus 4S plus 5. And if you want to cross check, you can also use this roots of 145 is -2 plus J, -2 minus J, just to cross check that everything is fine. Always cross checking is good. And then I'm displaying those coefficients, and from there I'll get the desired characteristic equation. So it is 145. So once I get the desired characteristic equation, I have to now compute the actual characteristic equation using this gains k1 and k2. So A is known, B is known, K is only unknown, two unknowns, and here I'll get two equations. So one unique solutions, two equations, two unknowns will solve for k1 and k2. So I have calculated bk. So it is 0, 0, 4k1, 4k2. A minus bk is given by this. Now I have to calculate it. I have to calculate determinant of Si minus A minus bk. So which is what I have calculated, and I got two equations with two unknowns, and then I have solved for k1 and k2, and then k1 and k2 are found to be minus 0.25 and minus 0.25. So in this way, we will be solving for these gains k1 and k2, and based on the desired pole locations, you will be able to solve. Now say if I have given -2 plus 2j and -2 minus 2j, accordingly the characteristic equation will change, and then we'll get a different k. And then if you see the K2 is responsible for this summation of the poles and K1 is responsible for the product of the poles. So in this way, we can also correlate, say, uh, the closed loop poles we are trying to place somewhere, and suppose we are making sure the product is same, but we are moving the poles in such a way the product is same, then k1 will remain same and k2 will change. Or if we try to keep the summation same and then say product different, in this way we are trying to do, say, we are changing the complex conjugate, so we are moving them up and down, so the summation will remain same because the real part is same and the complex part addition will get cancelled, right? So the we are moving them vertically. Then what will remain same? K2 will remain same because summation is same. And then product will vary, so the K1 will vary. So in this way, we can correlate which is varying what. And then we will also get that intuition that, okay, by varying this, these things are getting varied. Or by if we want to vary this, we have to change this. So in this way, we can see how the poles are moved. And then we are trying to, we have 2 degrees of freedom, right? Here we have K1 and K2. And based on K1 and K2, we can either move like this or like this. But because they're complex conjugates, there will be mirror image with respect to the x-axis. But in this way, we'll be solving and then we'll get the K1 and K2 unknowns. And then we can also correlate how they're related. Say if I let us consider one more small interesting practice. So let us, I'll change. What I will say is I'll give desired pole location is say different -2 minus 2j -2 plus 2j. Okay. So or I'll leave completely different. So I'll give -3 plus 2j -3 minus 2j. Again, it should be stable. That's why real part is negative. So -3 plus 2j -3 minus 2j. So I'll have -3 plus 2j -3 minus 2j. Okay. So what is the polynomial? S square plus 6s plus 13. So my polynomial is s square plus 6s plus 13. And I always like to cross check so that I don't end up making any mistake. So I'll do roots of coefficient. So -3 plus 2j -3 minus 2j. So this is, it looks like B. So let me, this is 13. Okay. And then this is 5 plus 4k2, right? So 5 plus 4k2, 5 plus 4k2 is 6. So k2 is 0.25. And then the other one is 6 plus 4k1. 6 plus 4k1 is 13, 5. So 1.25. So my k1, k2 is 0.25 and 1.25. So in this way, you can solve for K1 based on the desired pole equations. Yeah. And we can also change some value in the, say, transfer function. Instead of 5, if I give 4, then this will become 4. And then here this will become 4. And then accordingly you can solve. So you can also see by varying what parameter, what is getting changed, how much it is getting changed. So you can do all sorts of study based on this variable change or any parameter change. So is this clear until this point, Ravant? Any doubts you have? Yes, sir. Clear. Okay. So now let us solve the same thing, but now here it is like full order observer. And then they're asking it is L. Actually, it is L1 and L2. L is L1 and L2. And I'm not going into the details and the math, all those things, because that is already taught by sir. So I'll give you some state feedback controller, controller dynamics, observer dynamics. So controller dynamics are defined by A minus BK. A minus BK matrix. And then observer dynamics are defined by A minus LC. So since sir has already covered, I am not discussing it again. Rather, I would like to spend the time on the problem. So this is A minus LC. So we have to get the C matrix 1, 0, and A matrix is 0, minus A2, 1, and minus A1. And now you can see it is in observable canonical form. Okay. So again, we'll cross check or correlate with what we have learned previously in the last week. We'll go to the canonical forms. Yeah. So it is observable canonical form. So let us go back to our theory. So if you have this is the controllable canonical form, then it will become the transpose, right? Here y is say 0, 0, 1. There you will get 0, 1, 0, 0, 0, 1. So in this way, it will be changed. So it is like a transpose. So let us go back here. So I have not calculated the C matrix. C matrix is 1, 0, right? So here, there it will become 0, 1. It should become 0, 1, but why it is not 0, 1? Y of s, y is my output, 6y, right? Y is x1. Okay, just let me check why it is. Just wait, let me check. Yeah, 1, 0, 0 means it will become 0, 0, 1. So I think here also there is a mistake in the question. So it should be 0, 1 instead of 1, 0. Yeah, sorry for that. So instead of 1, 0, it will be 0 and 1. Okay. Yeah, yeah. Now it makes sense. So from the observable canonical form, you can get the controllable canonical form. You'll get the observable canonical form. So if this is my AB and where is C? Yeah. So if I do this, we know based on the transpose, you will get that. So this is observable canonical controllable, and from there we can get the observable canonical. So this is observable canonical form. Sorry, this is controllable canonical form. And this is observable canonical form. Okay. So I can write it, the dual of this. So it is 0, 1 here, minus 6, minus 5 here, x1, x2, plus 4, 0, and then y will be 0, 1, x1, x2, plus d is 0 into u. Okay, so this is AB. C and D. Yeah, got it. So in this way, we will be able to solve. So I got the ABCD matrices because I have considered the same transfer function. So no need to do it. We got the ABCD matrices. Now I have to calculate A minus LC. But before that, what is A2? What is A1? A2 is 6. A1 is 5. Hello, Manjula. Yeah. I think you might have joined a little bit late. We have covered so many topics, but it's okay. I'll be anyway uploading it, so you should be able to go. Manjula says, sir, I have not completed the 10-week assignment. So is there any solution for this? Because they will cut the marks in the college. Okay, you can contact the NPTEL team. As far as I remember, out of the 12 assignments, they'll take 10 best assignments, if I'm not wrong, but I'm not exactly sure. So you can contact the NPTEL team and ask regarding this. So even if you miss one assignment, I think it should be able to, you should be able to compensate in the other weeks. But just check the rules with the NPTEL team and then contact with that, because I don't have any control over this, and you should be contacting the NPTEL team only. So contact the NPTEL team and ask what will be the criteria for the final assessment, how much weightage will be considered from the assignments, how much weightage will be considered from the final exam, and how many assignments will be taken out of the 12. So they should be able to help you, and then you inform them why you have not completed the week 10 assignment, because I think the deadline is already over. So just check with the NPTEL team. I hope they will be able to help you. Okay, ABCD matrices are given. This 0, 1. Okay, sir. Thank you much. Okay. A2 is 6, A1 is 5. So let me write down. A2 is 6, A1 is A2 is 6, A1 is 5. Uh, yeah. So now I have to calculate A minus LC. So first let us calculate L and C. L into C. So L is L1, L2, and L is column matrix. So L is L1, L2, and C is 0, 1. So now I have to calculate LC. LC. So again, as I said, I have this confusion when I multiply with the matrices. So I do in the way I don't make any mistakes. So this is 2 cross 1. This is 1 cross 2. So final will be 2 cross 2. So first one will be 0, L1. Second row will be 0, L2. So this is LC. And what is my A matrix? A matrix is 0 minus 6, 1 minus 5. 0 minus 6, 1 minus 5. So A minus LC is 0 minus 0, 0, minus 6 minus L1, 1, and minus 5 minus L2. So this is my A minus LC. So now again, let us go back and see what they have asked. They have said the full order observer pole should be at minus 4 plus J, minus 4 minus J. So I have to first calculate the equation of this, but desired pole locations are given. So desired poles are given as minus 4 plus J, minus 4 minus J. Minus 4 plus J, minus 4 minus J. Now I have to get the desired characteristic equation. Desired characteristic equation. Again, I'll use the same MATLAB code. Let us not waste time. Minus 4 plus J, minus 4 minus J, right? So, minus 4 plus J, minus 4 minus J. Okay. So let us run to get the characteristic equation. It is 1, 8, and 17. So characteristic equation is given by S square plus 8, right? S square plus 8s plus 17. So this is the desired characteristic equation, which we'll be getting from A minus LC as well. But as I said, I'd like to cross check roots of coefficient. Minus 4 plus J, minus 4 minus J. Very good. Now let us solve for the A minus LC. Okay. So determinant of this. So I have to calculate the determinant of S minus LC. Determinant of S minus A minus LC. So we'll have S 6 plus L1 minus 1 S plus 5 plus L2. I have to calculate the determinant of this. And then this will be equated to the desired characteristic equation. Sorry. Okay, so let us solve. We will have S square plus 5 plus L2 into S plus 6 plus L1 is equal to S square plus 8S plus 17. So now we can get L2 is nothing but 3, L1 is nothing but 11. So in this way we can solve. So my L matrix is nothing but L1 and L2. So now using this observer, you can also design the controller A minus BK if they have given the poles. So here we have designed the observer. Say if they have given controller pole locations, then we'll use A minus BK and solve for the controller dynamics. In this way we can do, but I'm not going in the details. I'm just covering the observer as well as the controller. So let me just discuss or summarize this problem. Then I'll see if you have any questions. I'll summarize the entire session and we can end this discussion. So they have given a transfer function and it is in observable canonical form. So since we have already calculated the controllable canonical form, we can get the observable canonical form by considering the matrix dual. But we have to see that the controller dynamics are dependent on the matrix A minus BK and observable dynamics are dependent on the matrix A minus LC. So I got A, B, C, D matrices. L is unknown. I have calculated LC, then I have calculated A minus LC. They have given the desired poles. Then I'm checking the desired characteristic equation. Then A minus LC determinant of S minus A minus LC. Then I got the desired characteristic equation from the poles and I got the obtained desired characteristic equation in terms of L1 and L2. And again, two equations, two unknowns. I solved for L1 and L2. So the concept is simple, only you should not make any mistake and you should understand how you have to solve step by step. So this is more or less the discussion for week 12. And again, there will be one summary session tomorrow where I'll just cover what all I have discussed, just show the notes and then I'll just browse through the entire notes from starting to ending. So if you have any questions, you can ask, else I'll summarize today's session and then we can end this discussion. Any doubts? Okay, I guess no doubts. So week 12, we have discussed about the controllability, observability, state feedback design, as well as observer design. So controllability is that which in which we can change the states or we can transfer the states from one initial condition to another final state by means of the input. And in that case, the system is controllable. And to check the controllability, we have to check the rank of the controllability matrix, which is given by B, A, B, A square B up to son A to the power n minus 1 into B. And if the rank is equal to the order of the matrix, then it is controllable. If it is not, then system is not fully controllable. Some of them are controllable, some of them are non-controllable. So we have considered three problems. First two problems being second order and the third problem being third order. And in the first problem, we have seen the system is fully controllable, and we have seen in the second problem it is not. And then we have also seen how to get or find out which state is not controllable because there is no dependency on the input. And we have also seen that this second state is unstable and it will exponentially increase. And yeah, the uncontrollable system is unstable, so the system may become unstable. And in the third case or the third problem, we have considered a third order system and we have seen the rank is equal to the order of the system and all the states are controllable. And then we have moved to the observability which means whether we are able to measure all the states or not. If not, we might have to estimate. And the observability matrix is given by C A square up to so on C into A to the power n minus 1. Again, if the rank is n, all the states can be measured. If it is not, then we have to estimate the states, and using the observer as well as estimator, we can design the overall controller, observer based state feedback. And here also we have considered three problems, in which first two problems are second order and third problem is third order. And the first problem, the rank is full rank, or equal to the order of the matrix, and it is observable, whereas in the second case it is not, only one of them is observable and the other one is not. And the third problem, we have considered third order, and then we have seen the rank is maximum or equal to the order of the system, and it is fully observable. Then we have gone to the state feedback control, where we consider the input of the system to be a function of the states which are feeding back again to the system, and we'll write equal to minus kx because it's a negative feedback, and this k matrix is the unknown. So the input or the user will give the desired pole locations, which will result in the desired characteristic equations. Now comparing these two equations, we'll solve for k1 up to some kn. So in this problem, a transfer function is given. I have solved for the matrices A, B, C, D, and we have noticed it is in controllable canonical form. I got the ABCD matrices. Then I have solved for A minus BK, and based on the desired closed loop poles, I got the desired characteristic polynomial. And from the A minus BK, I got the equation in terms of unknowns k1 and k2, and then I have equated with the characteristic polynomial, and I got the k1 as well as k2. And here I have considered another such problem where I have changed the poles and I've seen how k1 and k2 are moving. And in the case of observer, it is also similar, observable canonical form. We got the ABCD matrices, and we know that observer dynamics are dependent on A minus LC. So I have calculated A minus LC, and based on the desired poles, I have calculated desired characteristic equation, and then I have compared to calculate L1 and L2. Say if the desired poles are slightly different, then you can compare and then you'll get L1 and L2. But the step-by-step guideline will remains the same. Only the answer will vary, but the entire process is same for any problem. So I think similar problems are given in the assignment as well. So I hope you should be able to do. If not, you can come back always to the uploaded YouTube video. You can see the concept, understand the concept, and then go back and solve it. Yes, so that is all about today's discussion. And again, we'll have 1 hour session tomorrow from 6 to 7, where I'll just quickly summarize all the concepts that we have discussed. Nothing much. So if you have any doubts, you can ask, else I'll end this session here. Revant, any doubts? No doubts. Okay. So in such case, I'll end this session here, and I wish you all the best for week 12 assignment, and thanks for staying till the end and making it interactive. I hope this session will help you in solving the assignments better, and hopefully you'll get good marks. And I wish you also all the best for your final exam. Go through all the concepts thoroughly, be confident, solve as many problems as possible, and get comfortable with the math. And since the videos are always there on the YouTube, you can always go through the videos if you face any difficulty, and solve as many number of problems as possible, and be confident for your final exam. So tomorrow will be my last session for this course, where I'll just quickly summarize what all we have discussed. And yeah, that's all about it. I wish you all the best, and I will end this session here. Thank you. Yeah, thank you. Good night, and all the best.